One of the things that we didn't mention was if a syncline or an anticline is not completely horizontal. What if it's tipped and flipped up at an angle? Well, these are some of the things that result on the surface of the Earth where an anticline is plunging down into the ground or up into the sky. So it forms these U-shaped features on the surface of the land. And if you looked at it from a cross-section from below, it would look like this. But on the surface of the land, it would look like these W's or these M's coming from the layered patterns of the rock layers. Well, Chapter 5, Section 2 is all about seismic waves and earthquakes. And this is a rather striking picture. As you know, Japan is in a earthquake hazard zone. They have the Kuril Trench, which is one of the deepest ocean trenches in the world, right off of the island of Japan, where subduction is occurring. And as we know from the nuclear power incident a few years ago, Japan is really at risk of another major earthquake happening. Well, what are these things that we call seismic waves? Seismic waves basically are a slip along a fault that carries energy from an earthquake away from the focus. The focus is the point underground at which the earthquake starts, and the epicenter is directly above that and on the surface of the Earth. And those earthquake energy waves, the seismic waves, carry that energy through the Earth's interior and also across the surface of the Earth. Well, there's different types of seismic waves. One of them is a P wave. It stands for primary wave. It's the first wave to occur in an earthquake. Primary waves are longitudinal. Remember when we did the slinky activity? No. The slinky activity was where we pushed on the slinky and a wave went in the direction of and an energy wave went in the direction that the wave was going in. It's a compression and expansion wave, kind of like an accordion. And the particles move in the direction that the wave is moving, not side to side or up and down. So it's a compressional wave. And there's a picture of what the slinky looked like if you were to take pictures of it over the course of several seconds on the left there. And the same thing you would see underground, compression and extension, tension and compression. Remember, tension is pulling apart. So that P wave, the initial wave, is compressional and tensional at the same time. And it's called a longitudinal wave. And I'll talk more about primary waves in just a minute. The second type of wave, the secondary wave, or S wave, are transverse. That means they go side to side or up and down. They go perpendicular to the direction of wave movement. So if a wave is moving from right to left, an S wave would move up and down or back and forth. So it moves in the opposite or perpendicular direction to the direction of the wave movement. This is the typical thing that you think of when you see an ocean wave. Okay, ocean waves are S waves. Surface waves are the third type of wave. P and S waves that reach the surface are called surface waves. Remember, the focus happens underground. So P and S waves, once they reach the surface, are called surface waves. When they get there, they start to move slowly. Okay, so the surface actually slows them down. They produce severe ground movement. Okay, severe ground movement, rolling or side to side movement. There's two types of surface waves called Raleigh waves and Love waves. The Raleigh waves are up and down surface waves, and the Love waves are a side to side surface wave. Well, a couple more facts on P waves and S waves. P waves are the first wave type created in an earthquake. They're primary. And they can travel through both liquid and solid. Okay. S waves, on the other hand, are secondary waves, and they are produced after the primary waves come. And S waves cannot move through liquid. For example, the mantle. They can't get through that liquidy molten mantle. They're reflected off of it, whereas primary waves go right through it. And here's a picture of P and S waves up here at the top. So P and S waves are felt here. Okay. Very weak P waves are felt over here. Only primary waves are here because they go through liquid and solid. Okay, here's a shadow zone in here. Here's S waves being absorbed right along this surface here. Okay, the S waves don't go through this liquidy, really super liquidy outer core here. Okay, so there's the S wave in purple and the P wave in blue. Okay? Well, scientists over the years have come up with many different ways of measuring earthquakes. One of the first ways to measure earthquakes was called the Mercalli Scale. It's a 12-step scale of intensity, from 1 being very low amount to 12 being catastrophic. And it measures the intensity at specific locations out from the epicenter. So as you can imagine, the strongest Mercalli waves would be right at the epicenter, and they would get lower and lower and lower as you move away from the epicenter in a concentric circle. Mercalli came up with some verbal descriptions that somebody could use to determine the size or strength of the earthquake. Number 2, feeble, noticed by only sensitive people. Number 3, slight, resembling vibrations caused by heavy traffic. So those are pretty light. If you kick down to number 7, very strong, general alarm and cracking walls are one of the characteristics of that level. If you kick it down to level 9, ruinous, the ground begins to crack and houses begin to collapse and pipes break. So going from one end to the other, you get a range of damage that when you see that damage, you know it's that level of earthquake. Okay, so it's not an actual measurement per se, but it's really a visual measurement. It's not using a scientific instrument, but it's just using visual inspection to figure out the strength of the earthquake. And here's a graphic of what I just said. All the way on the left, tables moving around and glasses falling off the table, maybe 2 or 3. Trees becoming knocked down. 6, people falling. Buildings crumbling is 8. 9, big giant cracks. 10, giant bridges and skyscrapers falling. So this is kind of a graphical illustration of that. Well, pretty soon people realized that that was only one way to measure it and less accurate. So the Richter scale was invented, and it's measured by recording the movement on the fault and the seismic waves. And it's on a scale of 1 to 10, not 1 to 12. And this is the scale from the U.S. Geological Survey. And you can see over there 0 to 2, not measured, not felt, very, very super light. 3 to 4, measured but not felt, sometimes felt, not much damage, light shaking, little damage, all the way on up to level 9, extreme destruction. The Richter scale was developed by Charles Richter in 1935, and it goes from 1 to 10. The interesting thing to remember about the Richter scale is that each step of the Richter scale, like from 1 to 2 or 2 to 3, is a 30-fold increase in energy. So a magnitude 9 quake is 800 times bigger than a magnitude 5. Pretty significant. Pretty intense. So it's actually called a logarithmic scale, where instead of going up in a straight line, it's a curved line of increase, where each time you increase it a little bit more and a little bit more and a little bit more. And here's what I mean by logarithmic. It's a curved line. So each time you move to the right on the magnitude scale, you're going up that much more. Okay? So you can see up there at the top, the largest recorded earthquake, 8.9, off the coast of Chile in 1960. By comparison, the Alaska earthquake of 1964 is that much lower, 8.9, a little bit closer to 8. The Great Earthquake of San Francisco is below that. The New Madrid earthquake in Maryland in 1812 was a giant earthquake, and that one is unusual and unexpected because it's a what's called a deep focus earthquake. It's not near any subduction zones or margins or anything like that, and made it very unusual. It's a different type of earthquake. I liked this graphic because it shows the amount of energy released compared to the magnitude of the earthquake. And as you probably can see there, the Northridge earthquake is right there, the one you're building a model about. And if you go up from the Northridge earthquake to Kobe, Japan, and then look right above there, 1989, that's us, the Loma Prieta earthquake. A little bit bigger, Charleston, South Carolina, 1886, and New Madrid, Missouri, 1811. The 1906 San Francisco earthquake is up there right almost at 8, and the Alaska and Chile earthquakes in the 60s up there in the 9 region. There's video of the Alaska earthquake that you can look up online. Pretty amazing earthquake. It was lucky that back in the 60s Alaska was not as inhabited as it is today, because it leveled everything. It was very, very destructive. And on the right there, it shows the energy equivalent in kilograms of explosive. So I'll show you, the next slide shows a little bit more how that works. And so you can see that the Hiroshima atomic bomb was less than the earthquake we had here in 1989. The Loma Prieta earthquake had more energy than the Hiroshima atomic bomb. Pretty amazing. Well, here is the scale in magnitude and how many happen per year. So this is the Richter scale. How many? Well, 3 to 4, less than 3 to 3.4. 800,000 earthquakes a year are less than 3.4 magnitude. Okay, and just noticeable indoors, about 30,000 a year, 3.5 to 4.2. So this is kind of interesting. Look down there at 8 and above, 1 every 5 to 10 years. Now that's pretty significant when you think about it. So every 10 years we have an earthquake of 8 or greater. That's quite a bit when you think about it. Okay, so expect in your lifetime to hear about or to be involved with at least 8 magnitude 8s or bigger. Okay, so if you live to be 80, right now you've experienced the Japan earthquake. Count that as 1. 10 years from now, 10 years from then actually I should say, in the world or locally, you will probably experience the next 8.0 or bigger earthquake. Okay? All right. So the next way of measuring earthquakes, the last one, is called the moment magnitude scale. and it's an estimate of the total energy released. And you can see there magnitude on the x-axis and energy released on the y-axis. And pretty interesting. The Loma Prieta earthquake is right in the middle. It released about 10 to the 22nd power of energy. 10 to the 22nd erg. It's a funny word. And erg is a unit of energy. I forget what it means, but on the total energy, remember Hiroshima is way up there. Hiroshima is actually right below 10 to the 22nd. So Hiroshima is right below the Loma Prieta earthquake in terms of the amount of energy it releases. And you can see up there the Chile earthquake in 1960. That's almost double the amount of energy. That's more than double the amount of energy of a Hiroshima bomb. Pretty amazing. Well, locating the epicenter is something that is actually fairly easy. You measure the difference in arrival times of the P and S waves. So there's the focus down in the middle, down on the ground, right along the fault line. If you travel straight upwards, you'll get to the epicenter. And from the epicenter, the seismic waves radiate out in concentric circles from the epicenter. Notice that the focus is right on the earthquake, and that this happens to be, what? Is this a normal fault or a reverse fault? Yeah, it looks normal. It's a normal fault. Well, how is it done? Well, let's take a look. If you measure the difference in arrival times for P and S waves at 3 different locations, you'll be able to calculate this way the epicenter of the earthquake. You have 3 concentric circles. You have 6 sets of arrival times of P and S waves, and you will be able to calculate the epicenter of the earthquake based on the average rate of travel of an S wave versus an average rate of travel for the P wave. I'm not going to go into how that's done, but it is pretty easy. Okay, that's it for the lecture for this. You're going to work on your models